last unit, we talked about objects, but most objects were like what? A car driving, right? Car was driving. A dog was running. A person was running. An alien spaceship flew. Okay? Most objects were in the horizontal direction, is what I'm trying to say. And that was the last unit. Now, before we started this unit, last week on Friday, we actually went outside with the tennis balls and golf balls, and we dropped them. That was the vertical direction. Now, before we dropped them, though, I wanted you to do one thing. I wanted you to do one thing because I wanted to tell you today on how that thing was really, honestly, of no importance to us. What was the one thing that you did before you dropped it? Before you found the height, you had to go get your whatever, tennis ball, golf ball, and you had to go over there by the library to the side on the ground, and you put it on the scale to take the measurement of the mass, right? You had to find the measurement of the mass. But did you ever actually use that mass number in the equation? Never did. Well, why did you make us do it? Because I wanted to talk to you this unit right now. This whole unit, we're going to talk about measurement still. We're going to talk about speed, velocity, acceleration. We're going to use those same kinematic equations that we used here. We're going to use them here, and we're going to use them here at the same time. Okay? So we're still going to talk about the same exact equation. So if they didn't stick in too good in your heart the first time, hopefully they really stick in this time. Okay? But again, though, mass is not important. And you're going to see on page 1 and part of page 2 when we're talking, I'm going to say repetitively, mass doesn't matter. The mass does not matter. Okay? It does not matter. Then the other thing I want to talk about is what do we do? We got those balls and we dropped them. So we were moving in the vertical direction. And even though we moved in the vertical and not horizontal, the vertical direction, we still use the kinematic equation, which was VI times T plus 1/2 AT squared. We still use kinematics. So we're still going to use kinematics on this unit, and so it's not going away. We're going to use it like if you drop something. What if, now here's the next thing that we're going to toss in. So we're still going to talk about objects moving horizontally. We're going to talk about objects being dropped. But what if there's a soccer ball and you kick it? What if you get a football and you punt it? What if you get a baseball and you throw it? So when you throw something, kick something, toss something, it moves in this direction. What is that shape in math class? Oh, semicircle parabola. We're going to parabolas, okay? And so we're going to use the kinematic equations with parabolas, okay? And that's what we're going to use today. But we need to understand why an object does what it does when it moves in a parabolic shape, okay? And that's what we're going to talk about today. So today's lesson is talking about why an object moves the way it does, or the velocity that it does, in a parabolic shape, okay? So let's go ahead and get started. The first word or definition for this unit is free fall. Okay? Free fall. So the definition of the word free fall in physics is in the absence of air resistance, all objects drop near the surface of the planet fall with the same constant acceleration. Now, in that one sentence, I need to make sure that I make a couple of clarifications, because so far, even though I made the clarifications, students in both other classes still said, well, what about da-da-da-da-da? Like they threw out this vocab word. And I'm like, oh, that's awesome that you know that word, but that has nothing to do here, because look, dropped near the surface of this planet, Earth. What do you mean by the word near? I mean, you were outside and you had that golf ball or tennis ball and you dropped, let's say you were standing on the ground and you're like, okay, I'm going to drop it from this location, measure this distance, and you dropped it. And then let's say you went up to the first set of stairs, the first flight of stairs, and you dropped it. Then you went up to the third flight of stairs and you dropped it. The dropped near the surface of the planet, I mean dropping it here in this location, or imagine the tallest building on planet Earth. Between this height and the tallest building on planet Earth, which is in Dubai. In Dubai. The what? The Burj Khalifa is the tallest building in the planet Earth. It's in Dubai. Because it's so tall, actually, it actually waves back and forth, and they built this thing inside of it that helps contradict the waves to cancel out the waves, because if not, the natural residence of the building will crumble on its own and just so that's pretty smart, whoever thought about that. But one more time, I'm talking about dropping it from here all the way to the tallest building on Earth. That's about the amount of distance I'm talking about. Now, if we get into an airplane and you're going to go and parachute off because you want to go and do something fun and exciting on your birthday when you turn 18, you want to just jump out and, you know, that's so cool. Well, then you know what? That's definitely going to be pretty tall. It's going to go probably a little bit higher than what I'm talking about. So in this class, we're talking about objects dropped near the surface of the planet. Now, I will use some examples of a helicopter dropping an object, but that helicopter is not going to be very high off the ground, okay? It's going to be fairly close to the ground. Now, it says here, though, imagine I'm over here, and I'm going to do a lot of like stick figure drawings for this unit because I'm a visual person. I need to see it. So you don't need to draw this. This is just me. So I'm over here, and I've got an apple, it says, and a feather. So here's my apple, and then it says I have a feather. Okay, there's Miss Munson. So I have an apple and I have a feather. I don't have an actual apple and an actual feather, but I think we're okay. I think we're big enough kids. You don't need me to have an actual apple and feather. But here's my apple and here's my feather. So I have an apple and feather. I'm holding them out at a certain height, and I'm going to release them at the same time. Now, when I release them at the same time, well, what's going to happen to them? They're going to fall, but who's going to hit the ground first? The apple, not the feather, right? I mean, duh, Miss Munson, that makes sense. We all know that's going to happen. So we know that if I was to sit here and drop an apple and a feather from the same height at the same time, that's a key point, at the same time, we know that the apple will hit the ground first. And the reason why that apple is going to hit the ground and why it takes longer for the feather to fall and hit the ground is because the air resistance slows down the feather, right? That air resistance. So if I have my feather over here and I'm going to say, okay, I'm about to just drop it, what's going to happen? It's going to go and slowly float and hit the ground because those air molecules are going to hit it and cause it to slow down. Wait a minute, going back to our lab, for those of you who are thinking, obviously the feather's going to hit slower than the apple because it weighs less, you're wrong. No, what did I say earlier? Nothing. I wanted you to take the mass because I wanted to make sure that I repeat it over and over. The mass has nothing to do with it. So if I have a feather and an apple, and they weigh significantly different masses, if I did not have air resistance, and I was in the absence of air resistance, what we consider to be true free fall, both the apple and the feather would hit the ground at the same time because mass has no significance in it. Now, when they both hit the ground at two different times, this went faster and this went slower, it had nothing to do with the mass. Had nothing to do with the mass at all. The reason why this went slower is because it's wider and it has a bigger surface area and the air molecules slowed it and hit it down. Kind of like a parachute for you, okay? So it has nothing to do with the mass of the object at all. Now let's go to the next question. The next question here, I personally have never been to the moon, but Oscar, I'm so sorry, Oscar. Oscar, is there air on the moon? You can breathe on the moon?
I mean, if you take tanks, you can.
Okay, but without the tanks?
Oh,
No. And if there is no air on the moon, ignore the tanks, the air tanks, then is there air resistance on the moon? If there's no air molecules? No, there's no air resistance. It's considered to be the perfect environment of what we call a vacuum, not a vacuum cleaner. So when I use the word vacuum, this unit, I mean like there's no air molecules. They literally, this air vents right here, they sucked all the air out of it, and we're all instantly going to die really fast. There's no more air. We're dead. Okay? That's what I mean by the word vacuum. They sucked all the air out. They shut the vents off. They sucked the air out, and we all took our last breath, and we died. There's no air. Okay? So in the moon, there is no air resistance because there is no air, and we call that a vacuum. And I'm going to use the word vacuum. So from here on out, in your minds, when we talk about problems, situations, equations, we're going to consider everything to be in a perfect vacuum situation, okay? Now, don't get me wrong. For those of you who want to go into aerospace engineering, for those of you who want to be pilots and fly one day, for those of you who want to go into mechanical engineering, well, in that case, then yeah, air resistance is important, and I need to mathematically calculate the air resistance, that friction. But in this case, we're not going to consider that a number in our calculations, okay? So remember, every problem situation is going to be considered in a vacuum. So it says here, let's watch a quick video. Because if we live here on planet Earth, which is not a vacuum, and the best location to do examples like this would be a vacuum. And so what's the closest natural vacuum to us? The moon.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we
No,
thought
that's
that,
literally
where would be a better
astronauts.
place to confirm his findings on the moon.
Yes.
And so we thought we'd try it here
No.
for you.
I'm writing a conspiracy
And the
theory
feather
about
happens to be
Galileo.
appropriately a falcon feather
Oh, they made it.
for our falcon.
Why would I?
And
I'll tell you in a
drop
minute.
the two of them here, and hopefully they'll hit the ground at the same time. How about that?
They hit the ground at the same time. Yeah.